So I'm going to continue the talk about the most important properties of molecular dynamics simulations, but I'm going to focus on transport properties. So before we start, I would like just to suggest some papers. So if you want to start with molecular dynamics simulations or learn more, there's a bunch of books, like very good books, but there are some papers like introductory material, and these papers are very good because they are kind of live papers. So they are never in the end version, like the final version. They are always updating these papers with new stuff. And the nice feature about these papers is because the authors gave you some links from GitHub, from Google Drive, and you can take some class or notes, slides about the technique. It's very good, it's introductory, but they take care about everything in molecular dynamics simulations. Also this one, that this is more like tips from molecular dynamics. So how to get self-diffusivity and viscosity without problem, doing like in the right mode. And also, last one, about sampling and errors. That is very important in molecular dynamics simulations. And if you don't do this, you can like calculate everything wrong and you just waste your time. And the last one is the paper from Frankel. He's like, he has the most important, or one of the most important books about molecular dynamics simulation. And in this paper, it's more like why do, where you do, why not do. So it's pretty good to start in simulations. So I'm going to talk about transport properties in equilibrium molecular dynamics. I try to do some like best practices and try to explain the methods that we have. So with MD simulations, equilibrium, sometimes non-equilibrium, we can do correlations with the experiment using transport properties. That is pretty good because we can do one simple simulation and see the direct correlation with the experiment. So it's pretty good. Easy to calculate. Sometimes it's not, depending of your material. But basically, almost all packages, MD packages, have everything to calculate transport properties. If you go to LAMP's manual and look to the compute function, you are going to see like a lot of properties that you can do. Gromax, you just type DMX -8 and you see everything. There is Travis, Pilot, MD, Python package, everything. So it's pretty easy to do, but we need to know the problems, we need to know about sampling and the theory about the calculations. So Professor Kalini told about autocorrelation function. So this is an autocorrelation function. So in autocorrelating functions, we are always comparing some property, some information in the time t with the previous time. And using this simple equation, we can calculate everything in time. So you just apply this for whatever you want. You can see the influence of time in your property. So using autocorrelation functions, we can see viscosity, diffusivity, velocity, our autocorrelation function, ion per lifetime, structural sampling. Kalini told you about this in her talk about the spectroscopy calculations, and the ionic conductivity using autocorrelation functions. So this is a classical autocorrelation function. In this case, is the interaction between two ions. So what we do, we calculate the property, look at the time, compare with the previous time. If the property doesn't change, we say that the autocorrelation function, the value is 1. If we see some change in the property, we say that's 0, and we have this decay to 0. And when the ACF decay to 0, we consider that the information is over, so you can calculate the relaxation time, the viscosity, diffusivity. And here is, I tried to do one example about what Kalini said. So she said that she used autocorrelation functions to do samplings in the trajectory. So we have the potential energy. So we do the ACF with the potential energy, and then we see something like this. So here we see that the ACF goes to 0, so something around here, 2000 picoseconds, 2 nanoseconds. So for this system, each 2 nanoseconds, the system loses the correlation. So if we sampling each 2 nanoseconds, we can take clusters without correlation with the previous clusters and use this for charge optimization, NMR calculations, quantum calculations. So autocorrelation functions like very versatile. And if we do the integration of the ACF, we can get the time of the property. So in this case, it's the same ACF from the previous slide, but this is just log scale. So when we do the integration to here, when decay to 0, I have the relation time, the relaxation time of this property. So the integration of the ACF, we call this green cubo methodology, but there is also another methodology that this is green cubo, and we can have viscosity, diffusivity, and ionic conductivity. And from another correlation is the Einstein method. So in the Einstein method, we use the derivative method. So we do linear fitting in the displacement of the property that we wanted. And we also can get viscosity, diffusivity, and ionic conductivity. Here's an example. So here we have functions to calculate self-diffusion coefficients using green cubo, Einstein method, shear viscosity using green cubo or Einstein method. So they should be equivalent. So we should have the same result using both methods. They require the same amount of data, depends on the system. Some systems, this is not true. The size of the simulation, the length of the simulation is different between them. I think green cubo is like more personal opinion. Green cubo is more easy to reproduce and more precise depending of the simulation of the system. And okay, let's go back. So we have green cubo and Einstein methodology. So we can use both, but there are some difference between them. Before you do the calculation, we have to take care about some stuff. So first, we have to use the correct ensemble because okay, let's go back again. So first, you have to choose the correct ensemble because if the simulation is not right, you can use it whatever you want, the method and software, the result is going to be wrong. You have to ensure that your statistical sampling is good. We have problems with the size box. So if you have a small size box, you not are going to see the real diffusive regime or the real property. One best idea to avoid problems and try to ensure ergosity is using different replicas. So in this way, we have different box with different starting point, so we can see different trajectories and get the average between the properties. And the first field, because if your first field is not good, any of these steps can correct the simulation. So always take care about the first field, see whatever you can do for the first field to improve the property. So here we have diffusion coefficient. So this is the green cube equation and the Einstein relation. In the green cube equation, we use the velocities of the atoms. So we use the velocity autocorrelation function. That is this graphic. So we see the decay to zero. And in the right, we see the Einstein method, or the mean square displacement, the MSD of the diffusivity. Okay. So here, those are pictures from the same paper. So those are the same simulations, but using different methods. So this is one example that we can do the same method for the same systems. And here, we have the results. So if we compare the diffusion coefficients for each ion in each ion liquid in both methods, we can see like some large difference between them. So in the first line, we have a 1.46 for the cation using MSD, and using green cube, the value is 2.9. And for the anion is 0.96, and the anion in VACF, the green cube, is 2.7. So they should be equivalent, but the values are different here. But if we look to the trend between them, the trend is the same. But the problem here is not because one method is wrong or the other is right. The problem here is because the simulation is not long enough to use the MSD calculation. In the green cube method, so we need to see the decay to zero, and this happens in very fast simulation. So if you look here, this is a simulation that has 1.5 picoseconds. So ACF is half of the simulation. So in this simulation, probably they have 3 picoseconds of length, but you need to save more often. So you have to fill all the points in the line. So you have to save almost each frame. That implies a high cost of the hard drive space. So you have to sample in uncorrelated frames. So the simulations should have 20 times longer than the decay time. So in this case, probably 20 picoseconds is enough to calculate. It's easier to reproduce because we have to integrate when it goes to zero. So it's easy to ensure that's going to zero. Mm-hmm. So it's because, so if you look at decay to zero pretty fast, so we need to save often to have a lot of points here. But when you do uncorrelate, you have a 0, 2, 1, 4, whatever, to try to avoid to count the property for a correlated structure. Because if you do this, you're counting always the same stuff. So you not see the real convergence. But even if we do uncorrelated frames, you can get the same points. So the uncorrelated frames just to avoid some wrong interpretation. It's clear? And in the MSD, it's different. In the MSD, we take the diffusion coefficient in the linear regime. So we need long simulations because dependent of the system is spending too much time to go to the diffusive regime. So we need hundreds of simulations. But in this case, we can save less often, 300 or 500 femtoseconds. Again, uncorrelated frames to improve the statisticals, long simulations. And in general, 10,000 of uncorrelated frames are enough to do the calculation. But the problem with the MSD sometimes can be misleading because of the convergence of the MSD. So here's an example of a MSD from an ion liquid. So if we look, we see 3 different regimes. So we have first ballistic, after a semi-diffusive, in the final diffusive regime. So the diffusion coefficient should be calculated here in the diffusive regime. And this is the problem, because if my simulation goes until here, I don't see this diffusive regime, and I have the wrong number. And this is the problem with the MSD in that table that I showed before. So one way to ensure that we have the linear diffusive regime is calculate the beta parameter. That's one way that we check the linearity here. So if the beta goes to 1, we have the diffusive regime in this region. So here is beta. So in this space, in this time, we have beta close to 1. So we choose this to take the diffusive regime. Another way is do the root of the MSD. If the value of this root is larger than the size of the box, this means that your particle can go and back in the box. So probably is in diffusive regime. Go to the literature and see what people do. And always discard the 10 first picoseconds of the simulations and the 10 last, because here's too noise and here's just the beginning. So 100% of certain there is no linear regime here. And if we go back to the column and look now to the beta parameter, we see that is far away from 1. So this is why they see a huge difference between VACF and MSD, because this is not in the linear regime.
Please tell us why the end of the line correlation no, you said in the last the end of the relation time it would be very hard. Why?
Oh, it's because when we do the calculation, we have some cumulative errors. So we are doing like the square displacement. So we are doing T1 minus T0. So when we go here, we don't have like too much statisticals, and we have a lot of cumulative errors. So this is just basic noise. And like if we do a zoom here, you can see like a huge oscillation of the points. So if you do the calculation there, probably your diffusion coefficient is wrong. So it's good to avoid the use the last of the simulation, the end of the simulation. So let's talk now about the collective properties. One collective property is one property that all the ions or atoms or molecules in the systems influence the properties. So like ionic conductivity, that we have pair formations, clusters formations. And the problem with collective properties is because it's not possible to do average between the atoms or the molecules. So this implies that these properties have a large amount of errors, of noise. So this can be hard to calculate using different methods, but it's possible. So here we have ionic conductivity using Green-Kubo correlation and Einstein correlation. So in Green-Kubo, we use the electrical current. So here J means velocity per charge. And here in MSD, we are using the dipole moment, so the mean squared displacement of the dipole moment. So it's position by charge. And if we look here, we see that this is the mean squared displacement of the atom I, and here J. So this is why it's a collective, because we calculate for both at the same time. So we have the correlation between them. So in the ACF, a classical ACF, the K to 0, so it's okay. And here the MSD. So the MSD for the ionic conductivity has more problems than the ACF. So if we look here in the green region, so this is just noise. So we should avoid this because there is a lot of cumulative errors. So this simulation has 320 nanoseconds, but after 20 nanoseconds, I have just noise. So I have to avoid all this part. And this is the problem with the Einstein relation. So if I'm working with like ionic liquids or polymer, a very correlated system, I need huge simulations, and like 2/3 of the simulation I cannot use. So here we spend a lot of calculations. But here in Green-Kubo, we need a smaller simulation, so just 1 picosecond, but we need to save amount of data very often, and we need to do a lot of calculations to avoid any errors here and to see the wrong decayment of the function. And so in the MSD of the diffusivity, we look to the end of the simulation. But in the case of the ionic conductivity of the MSD, we look to the beginning to avoid the errors. And here, one example about the comparison between the green Kubo conductivity, Einstein-Helfand, or MSD Einstein, and the experimental. So again, looking here, we see a huge difference between them. And sometimes green Kubo is the best, green Kubo is never the best here. So sometimes Einstein-Helfand is best, sometimes green Kubo. There's no like a rule, use green Kubo or avoid Einstein. You should do tests and run both and see which one is the best to you. Here is the viscosity, also green Kubo and Einstein relation. To calculate the viscosity, we use the pressure tensor. And here, Einstein, again, similar to the ionic conductivity, we take the fitting in the beginning of the slope, but in the autocorrelation function, we take the end. And here, both we can see like large fluctuations. So if you look here to the bars, these fluctuations. So which one I should use, green Kubo or Einstein? Depends to your system. Depends if you have experimental data, you can do comparisons to see which one is the best. You have to think about the code or the software that you are using. In general, for viscosity, people use green Kubo, but in Gromax, they say that the Einstein code that they have is best. So if you use Gromax, they say that you should use Einstein method. And also think about the machine that you have. If you can do like huge simulations, Einstein is okay. But if you cannot do huge simulations, maybe green Kubo is better, but you need a Monta hard drive space. So there are some ways to improve the results from green Kubo and Einstein method. And this is just improving averaging and doing some fittings in the equations. So here's one paper. So in this paper, they developed that they call a time decomposition method. In this method, they do like a lot of simulations. So if we look here, trash 1, trash 2, and trash 3, all are the same system, but with different start configurations. So if you look, the profiles are very different. So the values of the viscosity here are going to be very different. So what they do an average. So they have a more smooth profile. And in this case, they can ensure a better result. And if you go to like 100 of trajectories, you have an even more smooth profile. So this is best. So what they do here is they run a lot of simulations, calculate the viscosity for each one, do the average between them, calculate standard deviations. With the standard deviations, they do a fitting, calculate the fitting, and do again, and they do this. So if we look here, in red is the simulation data, and in the blue is the fitting. So if you look to the fitting, it's basically perfect, it's smooth. So you can have like here a pretty good result, but in this case, you need to do like 100 of simulations, so you need a lot of machining. In some cases, it's not possible. One way to improve green Kubo and Einstein method was developed in this paper. So they developed this equation, and with this equation, they can ensure that we have like here the convergence and also here. So since that you have the convergence and you know where is the convergence, you can calculate both green Kubo and Einstein method with a large certain. And here, if we compare green Kubo and Einstein-Helfand with the experiment, now we see a good correlation between green Kubo and Einstein-Helfand in diffusivity, ionic conductivity, and viscosity. Sorry. So we can use both methods, but we must ensure that we are doing in the right mode both methods, because if we do in the right mode, both are going to converge to the same result, or at least a close result. There's another way to calculate ionic conductivity that we call Nernst-Einstein, that we use just the diffusion coefficient from the simulations. And in this way, it's pretty more simple. It's just this equation that we can do like in the Excel table. But in this case, we don't have the correlation between the ions. We don't have pair formations, so we call this ideal conductivity, and this Eisenhofen or green cube we call real conductivity because we have the correlations. So when we have the correlation between one ion and his counter ion, so we consider that this is not carrying charge because it's zero, but here they are always carrying charge. So this is the maximum of the ionic conductivity that one system can have. And if we compare both, we have this Raven-Haven ratio. So that values go to 0 to 1. And using this, another simple equation, we can see about the formation pairs in the structure, the aggregates in the structures. So using this, we can see how much, not how much interaction, so how are the interactions if we have the formation of pairs or not in the system. And just to finish, I told you that with ACF, we can calculate a lot of stuff. So here, we use ACF to calculate ion pair lifetime and ion cage lifetime. So 8, we are looking to the distance between the central ion and the one ion in the solvation shell. And when the ion is inside of the cutoff, that is in general the first minimum in the RDF, we call this ion cage, and we consider that the cage is not broken, so the interaction, the solvation shell continues in the time, and here is the ion pair lifetime. So now we are looking to the distance of the closest neighbor to the central ion. So in both systems, we have the same equation, the same methodology. We're just changing our cutoff and the consideration of the pair. And using both, we can see the formation and the time of the relaxation ion pair lifetime. So again, to calculate transport properties, choose the correct ensemble in basically NVT. Ensure that you have a statistic and good sampling and long simulations. Look to the size effect. So you should do like a lot of tests here, run multiple simulations, change the box size, and see what happens. Use different replicas to improve your statistical. Look to your first field. Sometimes it's necessary to use a scale charge, sometimes it's not. And always study theory, because the codes here are pretty simple, and you can code a lot of stuff here. But if you don't know the theory, if you don't understand the way to do a good statistic and sampling, the result's not going to be good. So thank you.